All right, good afternoon. My name's Mike Beatty. I work with data center facilities. I've been doing that for about 12 years now. And for the 16 years before that, I was working with facilities like hospitals, commercial buildings, public buildings, industrial, food and beverage type facilities. And so we're going to talk about PUE and data center of the future. And actually some of the things that you're going to hear me talk about are somewhat of an echo of what Wim was talking about earlier. It's nice, I think, that we're all on the same page and openly sharing together. So when you look at the convergence, where we are today, and all of the things that are coming together, right? We have did a little bit of research, and if you look at Facebook, they have a commitment to reduce greenhouse gas footprint by 75%. Microsoft's goal is to cut carbon emissions by 10 million metric tons by 2030. We have obviously lots of lead designs and lots of new energy efficient developments. We also have, right, the convergence of the Internet of Things, the edge data centers, all this being talked about what's going to be happening, 5G rollout and how much more compute intense 5G is going to be. The technology that we have now regarding liquid cooling and the temperatures that we can run liquid cooling, we are at this wonderful moment of this convergence where we can bring all these things together for data center heat recovery. It's very practical. There's no major new technology or development that needs to be put together to actually make this happen. I like to say that our brethren in Europe they're pretty far ahead of where we are in the United States. But I think that needs to change, and this is part of a challenge to companies in the United States to step up and say, how do we start doing this type of energy efficient design to reuse the excess heat in data centers? So we have the technology. These are just a couple of the companies that have developed solutions for excess heat reuse. Asperitas, we heard from earlier, has solutions in how to do this with immersion cooling. There's a lot of different vendors. It's not like it's proprietary to one different company. There's choices to where you can choose to use water, and for those who are very averse to use water, there's plenty of dielectric fluid options available to recover this heat. So a lot of these equipment items, I know Wim talked about how they've looked at temperatures of 65 degrees Celsius and see that as yeah, they can work with those kinds of temperatures. I know Liquid Cool has done extensive testing and has no problem with 140 degree Fahrenheit fluid coming out of their servers, their enclosed encapsulated servers. So I think there's some education that has to occur in the data center community. When people hear 140 degrees, right, they might get a little nervous and, hey, wait a minute, right? ASHRAE says, you know, our limit is this, but liquid cooling is very different than using air cooling. It's much more energy efficient, has so much more of a higher heat capacity, so it's much more effective. The key point is that microprocessor you need to keep below 95 degrees Celsius. It takes a lot of air to make that happen, a lot less liquid, and so you can run at the higher temperatures with the liquid. Now, in the United States, typically older buildings have used 180 degree Fahrenheit hot water systems. This is a very typical construction design, using hot water boilers and circulating at 180 degrees. But with the changes that have been occurring over the years, now they're using different hot water temperatures because they're more energy efficient just for your regular commercial buildings, your retail, your shopping malls, hospitals, schools, whatever that might be. And so those systems are using 120 to 140 Fahrenheit or 49 to 60 degrees Celsius water. So we're not far apart here, folks. We're right in this perfect time where it's practical to take a small data center and use it to heat a building. Now this diagram was courtesy of Liquid Cool, but it just shows the flow path. You'd have the Liquid Cool server racks, and you'd be returning fluid coming back around 122 Fahrenheit and pumping out fluid at 140 degrees Fahrenheit. So you'd have an array, let's say, of valves, and you have the choice where if you don't need building heat, well, you can send it to a dry cooler, a rather inexpensive solution to reject the heat in that way. And if you do call for building heat, you simply need to put a heat exchanger. From the design of a commercial or public or government building, to add a heat exchanger into the building heat loop is really not much of a cost. There's a very low capital cost just to add that. So again, going back to this is a very practical solution, and there's no reason why we shouldn't be seeing and doing more of this in North America, in this continent. Wim touched on this a little bit. His formula was a little different than mine, but basically, PUE, we're thankful to the Green Grid for developing PUE. I think it's been a very helpful metric for all of us to gauge things and how we're doing with energy efficiency. And I just call this a heat recovery adjusted PUE. Why make things super complicated? We just take the facility power, and we have a conversion factor between BTUs and watts. So let's just convert that, and whatever we would be able to recover to reuse heat in a facility, use that for the calculation. Now, I met a young fellow from the Caribbean here at the summit. In the Caribbean, you're probably not going to reuse much heat, right? It's already pretty hot down there. But I'm from Pennsylvania in the northeastern part of United States, and I can tell you there's an awful lot of demand for heat, especially now. It's kind of snowy and cold when I left. So it's rather simple. The technology exists. We have this. It's with multiple vendors. I think one of the things that I like a lot about, and it doesn't get discussed a lot about immersion cooling or liquid cooling in different ways, is there's less exposure to dust. There's less exposure to things that can get in there and cause problems with the electronics. So in a number of ways, it's a cleaner way. And I think you'll get longer IT equipment life by using the liquid cooling type technology. From a mechanical aspect, for this type of solution, there's very few moving parts. You have some pumps, and you also have some dry cooler fans. I mean, as far as actual mechanical moving parts, these are items that can be inexpensively and easily stored at a site, so that if you had one fail, that you could go and replace them. No compressors, no chillers, no cracks, and no airflow issues. So, I mean, these are things that people have dealt with in enterprise data centers for years and years and years. This is another, I think, great point to point out, is there's no water usage. That new parameter, or relatively new water usage effectiveness, the WUE, it's more important in some geographies than other, but especially in California, Nevada, Arizona, I mean, water usage is really important. Adiabatic cooling is very energy efficient, but it uses water. Chiller plants with cooling towers are fairly efficient, but they use water. With this kind of solution, you could put a data center in Death Valley, and if it gets up to 120 degrees there, you got fluid coming out at 140. You can still cool it in 120 ambient air temperature. So it's just a wonderful type of solution that can be applied in a lot of geographies. Rather than jump into all kinds of different buildings, I just picked out schools. And so this is a busy slide. I got the information on this, most of it from the Energy Star Data Trends Energy Use in K through 12 schools. But this is a survey that people participated in 55,000 schools. So this was the median size. And basically, I took this information to get to roughly how many metric tons is that. So 55,000 schools contribute almost 23 million metric tons of carbon dioxide greenhouse gas every year, okay? Every year. Now here we go. Here's another interesting statistic is right now there's about 132,000 public and private schools in the United States alone. It just gives you an idea of how many schools are out there. So let's go back to Microsoft and their goal. They want to cut 10 million metric tons of CO2 by 2030. Well, if we just, let's say we took and heated 1,500 schools. Say there was a goal to start doing this. And again, it doesn't have to be schools. It could be any kind of building. And use edge data centers to do that. Well, that would eliminate over 6 million metric tons of CO2 over 10 years. That's a pretty big amount. So my point is there's an aspect, let's call it maybe double dipping, where they're going to you want to use renewable energy for these data centers, for these edge data centers where you want to recover it. So why not get the additional benefit of eliminating the natural gas or the fuel oil or other types of fossil fuels, and that would benefit these companies corporately in achieving more of their greenhouse gas emission reduction goals. I put down here just some comparisons as I was analyzing. I'm not going to go through them all, but it just gives a rough idea for different types of buildings and how many metric tons of greenhouse gases you might expect from a building like that. A number of years ago, I did an upgrade project for a major shipping and logistics company, and as was interesting was their data center was in one of their warehouses. And so we did that upgrade and we put in DX cooling. So it's kind of sad because you had all that heat and it's just going out in the roof when, if you had a system like this, you could actually take some of that heat and recover it and heat that warehouse. So it's very practical. There's really no reason why we shouldn't be doing this. I think that part of the need is somebody to step up and say, you know what, we're going to make the commitment to do it first. And that's where we're looking for. I think we need to see more companies step up to do this in North America. There's another interesting chart that shows from the University of Michigan here for sustainable systems. And it just shows the typical breakdown of heat and energy being used in buildings. And then it compares that on the chart. So schools, education is really only down here. They're not one of the highest densities when it comes to thousands of BTUs per square foot. And there's other buildings up here that, especially hospitals, that use quite a bit of energy per square foot. So again, schools, I like schools, right? We all have kids, they go to school, and we want to support our local schools. I just thought that was a good one to look at. But the truth is, commercial buildings, lots of other buildings, this is a real practical idea, especially when we've been hearing at this summit that the amounts of edge computing that are going to be happening in the future are going to skyrocket. If people are going to do AI type computing, that's going to be a huge demand. So I think there's a lot of good practical things that go into this kind of concept. There's a lot of win-wins, I feel. Right? I like it when vendors and customers have good relationships and work well together and have great solutions. And with this kind of idea, there's a number of marketplace clients to work with here, but there's a number of win-wins, right? Obviously helping to reduce carbon emission reductions, helping the environment. One customer might want to offer a data center and give the heat for free, and in exchange for that, if we're heating a school, they don't have to pay any taxes. They don't have to own the land. There might be other financial benefits for that company to put a remote data center, an edge data center, by a school. The other thing would be shared generator and generator services, right? If you're going to build a 2N generator type design, And you might offer to the school or the customer, hey, we'll share this with you, we'll share the cost. So there's a lot of aspects, I think, and this is just a couple, but I think there's a whole lot of aspects of potential negotiation between real estate locations, potential customers, cloud providers, anybody who wants a private cloud where they want to use private cloud for certain buildings or certain locations. There's really a huge number of potential solutions here, and I think we're just beginning to scratch the surface, and we want to popularize this idea because it's very practical nowadays. There's still, I think, some more things to work out here. I think we need to work out some standards. What does this look like? And I love the OCP community. It's about being open and sharing how do we do things. Some of the key things is, capacity needs. What does that look like? How much should I build out an edge data center for that building? Should I provide all the heat? What would a service level agreement look like? I mean, there's a number of things to try and work out and discuss to work out with people, and what does that look like? I think also for the scenario that I showed for using a dry cooler and a heat exchanger, there's some work on developing algorithms and things so that you don't want to have large delta T's in short periods of time across your server equipment. You don't want that temperature change in 10 degrees in like 5 seconds. That would be a problem. You just have too much contraction expansion too quickly that way. So there's some things to work out in this. Also, PUE calculation and monitoring, the simple way, it's been done for years, I'm a fan of it, is flow and temperature. Very simple, there's very good sensors to be able to do that, and that's how you could figure out what your reduced PUE is. Possibly rolling virtual workloads where if a building requires more heat, you could roll some type of virtual load to that if that works into a solution. What are the redundancy requirements? Is N+1 adequate? Do I need a 2N? These are all kind of things to be talked about long term. And then as well as security requirements. What would be needed to make sure that this building would be safe and would not be at risk for any kind of intrusion or anything like that. So how do you get involved? Well, I've been talking with Brevin. Brevin's just been wonderfully supportive in helping to get new things and initiatives going in the OCP community. And so the question is this something that people would want to commit to? Is there an interest in the OCP community to step in and begin working together for recovering excess heat from data centers and looking at different designs to make this a priority and actually get some case studies in place? I think that's the first goal. And as we do that, then we share what we've learned, what we can improve, and I think it begins to then popularize this idea of we're growing the edge, we're growing what these data centers are, so now we can begin sharing information. And I think especially educating the engineering community and just in helping engineers, because engineers typically are involved when building with these new buildings, so they know what can be done and what are some good best practices for that. Okay, so that's it. Does anybody have any questions? No? Okay. Yeah, question?
Sorry, says questions.
Yeah, you did a good job of presenting the case of integrating the data center into the community and being a good neighbor from the water side and using using the heat that's discharged from the data center to be used by the community around it. What about the electrical systems? How can a data center effectively share the power demand that it has in a way that is a contribution to and or beneficial to the community around it?
Yeah, I think that's an excellent point. And I'm just scratching the surface on that, but I think shared services for equipment, emergency generator, backup power, if you go with a 2N design, then there could be a way to share that. You could put in paralleling gear so that your data center would be your first critical point. But then if there was a loss of utility power, then you could have one of the generators help to power the building or whatever that client is. So that would be one solution. And even if you had a generator fail in a situation like that, you could put a quick connect in to bring that in as well. I think from what I've seen with hyperscalers and some of the large providers, that one of the primary goals is how do we use renewable energy, right? Wind and other types. So I think that just kicks off a whole new level of additional discussions and projects in that way.
Yeah, very good answer. And moving along in that same direction, the use of on-site power generation is a great opportunity for a community to use either natural gas turbines with cogeneration or trigeneration behind them, and or on-site solar and or wind for the community to be shared with a data center through a microgrid, where the microgrid would continuously select the most economical, available, and best power for each one of the different facilities in the community.
Absolutely, yeah. I think there's a whole host of potential solutions out there, but I think as we start generating interest and more engineers are looking at, okay, well, this sounds great, I'm going to build a building, who would want to build a data center to work with my building? I think we're going to get more experiences and be able to share more, especially in this community. So that's what I'm really looking forward to. Okay, any other questions? No? Great. Well, thank you all for attending. I appreciate you coming.